For most of the 19th century, chemists operated on a simple assumption. If you could zoom in far enough, you would find that all matter was made of tiny, indestructible spheres. They pictured atoms as solid objects, much like microscopic billiard balls. That consensus broke in 1897. Using a sealed glass tube hooked up to an electrical source, J.J. Thomson discovered that atoms actually contained much smaller, negatively charged particles, what we now call electrons. To make sense of this, scientists developed a new working concept. As this diagram illustrates, they envisioned the atom as a sphere of positive charge, with the negative electrons embedded randomly throughout it. They called it the Plum Pudding Model, but you can think of it like blueberries stuck in the dough of a muffin. Thomson had proven these subatomic particles existed, but he hit a physical wall. He had absolutely no way to isolate a single electron to measure its actual charge or mass. You cannot grab an electron with tweezers. You cannot scoop a handful of them onto a laboratory scale. They are simply too small and too fast for any macroscopic tool. Physicists knew the electron was there, but they needed an exact mathematical value for its charge. Without that specific number, the actual mechanics of the atom would remain a complete mystery. To get that number, scientists had to build elaborate physical traps, forcing these invisible quantum fragments to fight against everyday forces we can actually measure. In 1909, Robert Millikan and Harvey Fletcher built exactly that kind of trap. They constructed a sealed, multi-layered metal and glass chamber designed to isolate a single microscopic object. The device started with a surprisingly mundane piece of hardware, an atomizer. Working exactly like a vintage perfume mister, it sprayed a fine fog of oil into the top of the chamber. As we see in this cross-section, tiny droplets drift downward through a small hole. Gravity pulls them toward the bottom. While drifting, some drops scrape against the air and lose electrons, leaving the droplet with an overall positive charge. By creating a charged droplet in freefall, Robert Millikan successfully isolated the exact variable he needed to manipulate. The bottom of the chamber featured two metal plates connected to a power supply. Using precision analog dials, Millikan could send an electrical current into those plates. This setup creates a microscopic tug-of-war. The positive charge on the bottom plate creates an upward electrical push, while gravity pulls it down. By adjusting the voltage, the electrical pole neutralized gravity entirely, freezing the droplet in midair. Millikan repeated this freezing process for dozens of different drops of different sizes. When he calculated the electrical force required each time, the results were always a multiple of one incredibly tiny number, 160 zeptocoulombs. Because the drops could only lose electrons in whole numbers, that common denominator had to be the charge of a single electron. Pitting electricity against gravity allowed Millikan to capture a precise number for an invisible particle. Knowing the exact charge of the electron immediately prompted the next physical challenge. Ernest Rutherford wanted to know how those electrons were arranged around the positive charge inside the atom. Rutherford built a new trap. As outlined in this schematic, his team used a particle gun to fire tiny, positively charged subatomic bullets at a sheet of gold foil. They surrounded the foil with a circular screen that flashed whenever a particle hit it. Looking at the particle paths, almost all of them tore straight through the gold. But every once in a while, a particle hit something so hard it ricocheted violently backward, striking the detector right next to the gun. That violent bounce destroyed the old muffin dough theory. The only way a positively charged bullet flies straight backwards is if it strikes something incredibly dense, hard, and positively charged, proving the existence of a solid atomic nucleus. These experiments verified a new reality. The atom consists of a highly dense central nucleus, surrounded by electrons whipping through a vast empty void. Today, we associate subatomic physics with massive supercomputers and endless equations on chalkboards. But the exact physical structure of our universe was initially mapped using perfume misters, chunks of wax, and thin sheets of hammered gold. These tinkerers physically engineered a path into the unseeable, using mechanical ingenuity to force nature's deepest secrets into the light.